Okay, so going back to the lecture. The objectives for this lecture is I want you to learn or to understand and describe sample spaces and events for random experiments with graph, tables, and 3 diagrams. You're going to learn what is a permutation and what is a combination to count the number of outcomes in both an event and a sample space. Then you're going to learn how to calculate the probabilities of joint events, such as unions, intersections, from probability of individual events. And you need to interpret and calculate conditional probabilities of events. And the last learning objective is to determine the independence of events and use that concept to calculate probabilities. So let's start by discussing what is a random experiment. So the goal of random experiment is to understand, quantify, and model. Guess I'm using the wrong presentation, sorry. There you go. The goal is to understand, quantify, and model the variation affecting a physical system behavior. So again, as engineers, we're going to be dealing with models. We want to create models to represent the reality, and we're going to use those models to run some experiments in order to make some recommendations about the real system. One way to do experimentation is to use the real physical system, but that's too expensive. You don't want to be trying several things in your real experiment and then find out that what you're trying to do is not effective or is not providing you with a good outcome. So most of the time what we do is we create models to represent the real system. We run our experiments using those models, and then we can find out what is the best way to manage or to operate the system, and then we can implement those recommendations in the real system. So the model is used to analyze and predict the physical system behavior as system inputs affect system outputs. The predictions are verified through experimentation with the physical system. So again, we're going to use the physical system. We're going to get some measurements based on the data that we have about that system. We're going to create a model. And using the model, we're going to perform some analysis, some experimentation that will be tested again using the real system. So this is an interaction that is continuous between the real system and the model and the real system. So the other thing that you need to know is that noise is something that will affect your real system. And that's why we need to take into account random events. So random values of the noise variables cannot be controlled and cause the random variation in the output value. So if you have a system and you know, let's say this is a car, you buy a car, you want to use your car for 10 years. If your car is a perfect system, then you know that the car will not break at any point. You will not have to perform any maintenance to that car because you know that this is a perfect system and it's not going to fail. We all know that it's not true, right? So we know that there's some noise variables, some random variation. Could be the environment that is going to be affecting this system. And at some point, if you don't perform any maintenance, you're going to have to fix your car because of something happening. Okay? So hoping to control inputs constant does not keep the output values constant. So you have your system, You have some control variables, so you put gas, you change the oil every 3 months. But there's also other variables. It could be you crash your car or something else that would determine what would be the output of your current system. So there's some things that we can control, but there are other things that we cannot control, and that also will affect the performance of your system. Okay? So those variables affect the transformations of the inputs to the outputs of the system. Okay, so a random experiment. An experiment is an operation or procedure. It's carried out under controlled conditions. It's executed to discover a known result or to illustrate a known law. An experiment can result in different outcomes, even if repeated in the same manner every time. It's called a random experiment. So let's say you want to toss a coin. You can get a quarter. You want to toss that quarter. You can toss it the same way, but you know that every time you toss that coin, you are not guaranteed to get the same outcome. And that's a very simple example of an experiment. Same thing happens if you want to throw some dice. You'll see that even if you throw this in the same way, you are not guaranteed to get the same outcome every time. Another example here is, this is more technical example. So if you think about telephone systems and you're managing this system, you need to make sure that you have sufficient capacity or number of lines to handle a number of callers at a random point in time, whose call has a random duration. So let's say you're managing your telephone system and you want to run this system with 3 lines. What will happen if you at some point in time you have more than 3 calls? You're going to have to drop some of those calls, right? Because you can only handle, you have capacity for only 3 calls. So this is the type of situation that you can manage or you can plan if you use probability models. So you can easily take a look at your historical demand and find out what are the time periods in which you are expecting more calls. So you can basically plan for those time periods and have extra capacity to manage all those calls. Okay, so let's think about this specific scenario in which we have calls arrive exactly every 5 minutes and last for exactly 5 minutes. So if that is the case, let's see that the situation is just like this. So you have every 5 minutes you have a call. So let's look at this timeline. So the scenario that we're talking about is like you're going to receive a call every 5 minutes. So this is 5, this is 10, this is 15, this is 20. And you know that each call, the duration for each call is 5 minutes. So you know that at the end of 5 minutes, you will finish the first call. And then after that, you're going to have the second one, third one, and fourth one. So in such case, such a scenario, you only need 1 line because you know that each call is going to finish before the next call enters the system. And we know that that's not reality. That's not what really happens, okay? So if we look at the real thing, you know that sometimes call will last less than 5 minutes, but there will be some calls that will last more than 5 minutes. So in such cases, you're going to have some overlapping between calls. And for such cases, you need to plan to have more capacity. Okay, so again, times between calls are random, and the call durations are random. So calls can come into conflict. Let's look at the next figure here. So in the top system is the same diagram that I just showed you. You have calls arriving every 5 minutes with the same duration. So we know that at the end of the first call, you're going to be able to take the second one. At the end of the second one, you're going to be able to take the third one, and so on. But in the bottom system, call has random duration. So the first call, the duration is about 1.5 minutes. But what happened? The second call lasts more than 5 minutes. So when the third call arrives, it is blocked because you only have one line. And that's what you need to, as manager of such a system, you need to avoid to have such a situation. Okay, so that being said, you know that we have random events that happen. You know that you need to take into account those random events when you're planning for your system, so you can have your system operating in the optimal conditions. Okay, so now we know what it's a random event. You know that we can have random durations. Now let's talk about what is a sample space. Again, a sample space is a very important concept in probability. When you know how to establish or how to list the events of your sample space, then you are able to compute the probability. So, starting with an observation is any recording of information. It could be numerical or categorical. For example, the number of accidents that occurred for each month from January to April. It could be 2, 0, 1, and 2. So this basically is saying that in January we have 2 accidents, February we had 0, and so on. April we had 2. So random experiments have unique outcomes. And as a definition of a sample space, the sample space is the set of all possible outcomes of a statistical experiment. So when you are able to list all the outcomes, then you can basically list or establish your sample space. Again, the set of all possible outcomes of a random experiment is called the sample space, and we use capital S to denote our sample space. Do you remember what else we were denoting with an S? Correct, the standard deviation. But again, remember that now we're talking about probabilities. So when we talk about probabilities and I ask you to define your sample space, you can denote the sample space using S. Each outcome in the sample space is called an element or a member of the sample space, or simply a sample point. The sample space is discrete if it consists of a finite or countable infinite set of outcomes. So if you can count the number of elements for your sample space, then you can say that you have a sample space that is discrete. On the other side, if S is continuous, if it contains an interval of real numbers. So in such a case, you might not be able to count the number of elements for your sample space. Any questions so far? Again, these are very simple but very important concepts. First, learn what is a sample space, and we know that for a sample space we're going to have some elements or members that are called sample points, and then we're going to learn how to establish or how to list the element of a sample space. So let's look again to these examples. So I already talked about the toss a coin example. So the sample space of possible outcomes when a coin is flipped may be written as the sample space equals head and tails, because those are the only two outcomes that you can have for such an experiment. You toss a coin, it could be head or tail. There's nothing else that can happen. So that basically defines your sample space for such an experiment. Now let's consider the experiment of tossing a die. If you are interested in the number that shows on the top face, anyone can tell me what the sample space will be? If you are interested on the top face of the dice? 1 to 6, correct. So the sample space is basically numbers 1, 2, 3, 4, 5, and 6. Because those are the only outcomes that you can see in that. If you're interested only in whether the number is even or odd, what will be the sample space? So again, we are defining our outcomes as even or odd. Those are two outcomes, which means that your sample space is going to be defined by those two words, even and odd. We know which numbers are even, we know which numbers are odd, but the experiment is actually trying to find out how many times do you land a odd number, or how many times do you land a even number. So in such a case, then you can define your sample space as even or odd. Those are the only two outcomes. Any questions? Okay. Okay, so now think about this other scenario. So suppose that 3 items are selected at random from a manufacturing process. Each item is inspected and classified defective or non-defective. So you're going through this manufacturing line, you want to find out how good your process is, and the only way that you can find out how good your process is by sampling your product and finding out if you are producing most of your items non-defective items. So you go, this experiment is basically looking at 3 items that are randomly selected from your manufacturing process, and I want you to define the sample space for such an experiment. So if you think about the first item, you grab the first item, what is the only 2 options that you have for that first item? Exactly, defective, non-defective. Okay, very good. So now you have to go and check the second item. What are the outcomes for that second item? Defective, non-defective. Same thing for the third item. Defective or non-defective. So for that type of experiment, we can list the options or the outcomes for the experiment using a tree, which is represented right here. This is what we call a tree. So what we're trying to do is to define our sample space by using this diagram. So as you can see at the top, we have first item, second item, and third item. And what we're doing is, for the first item, we know that it can be defective or non-defective. But we know that if it is defective, the second one can be defective or non-defective. And also, if the first one is non-defective, the second one can also be defective or non-defective. So you start with the first item, then you list the options for both branches. And then when you get to the third item, you have to list the option for the third item for each outcome of the second item. So at the end, you're going to end up with 1, 2, 3, 4, 5, 6, 8 branches. Okay? And then you can list a sample point for each branch. So this one is D, 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 which means that you have 3 defective items in this experiment. So the sample point for that one is 3 Ds. Now, if you go through this branch, you will have D, D, and non-defective. So the outcome for that experiment is 2 defective and the last one non-defective. And you can do the same thing for all the branches of the 3. So this one, defective, non-defective, non-defective. this is another possible outcome for your experiment. So if you go, you select 3 items from your manufacturing process. These are the only 8 outcomes for that experiment. It could be any of those, but those are the only options that you will have. You cannot have any other outcome for that particular experiment. Okay, so either you have 3 defectives or you have 2 defectives, non-defective. It will depend also on the order in which you select the items. So the sample space for this particular example is basically listing all the sample points for the experiment. So you have 8 outcomes for this experiment. Any questions? Okay, so I want you to start thinking about this because you're going to have a lab today and you're going to apply some of those concepts in the lab. So the better you understand, the more questions you ask, the better you will do in the lab. Okay? So, any questions? Okay. So I have another example. It's basically another scenario in which we have messages that are classified as on time or late, and you are basically looking at 3 messages. So again, you want to list the possible outcomes for these 3 messages that you're looking at. So it could be on time or late. So again, you're going to have 8 outcomes because you're going to have 2 options for each item or for each message. So you have 2 options for the first message, 2 options for the second message, and 2 options for the third message, which means that you're going to have 2 times 2 times 2 equals 8 outcomes. So in the same way, you can list the outcome for the experiment, on time, on time, on time. That's the first outcome. You can also have on time, late. You can have on time, late, on time, late, late, and so on. So once you're able to draw these 3, the only thing that you need to check is what are going to be the combinations at the end. So this is going to be your first outcome, this is going to be your second outcome, and so on, until you list the 8 outcomes. Any questions? So for example, if we try to show you the importance of having such, or to define, the importance of defining a sample space. So for example, so this is going to be the first outcome, on time, and on time. And this is going to be on time, late. And this one is going to be on time, late, on time. I can ask you, what is the probability of having all of them on time? Correct. It's going to be 1 over 8 because you have 8 possibilities and you're trying to pick 1 out of the 8. So the chances of having all the messages on time is going to be 1 over 8. Okay? So if you are able to list your sample space, then you can compute the probability for an outcome. Okay? So if you're trying to, if your boss tells you that the maximum number of messages that can be late is 1, then by having the sample space, you can compute the probability of such an event happening. So you can look at the number of times that you only have more than 1 late message, and then compute that probability and see if your system is performing as expected. If not, then you're going to have to make some revisions and improvements. Okay? So again, here's the sample space. and we have 8 elements, and they're listed basically at the bottom of 3, so you can list them here for the set. And this can get very complicated. If we have, the more options we have, the more difficult it's going to be to list all the outcomes of your sample space. So here we have a different example in which you have a new cars can be equipped with selected options as follows. So you can decide whether you have a manual or automatic transmission with air conditioning, 3 choices of stereo sound systems, 4 stereo choices or color choices. So again, if you have 2 options for the transmission, these are 2 options. 2 options for the AC, 3 options for the stereo system, and 4 options for the color or the exterior. Then you're going to have 2 times 2 times 3 times 4 outcomes, which is equal to 48. And we can list them. I mean, 48 is still doable, so you can list automatic and manual, air conditioner, yes or no, type of stereo, 1, 2, 3, and then the color, 1, 2, 4. So what are the chances that a customer will request a car that is with manual transmission, air conditioner, the first type of stereo, and red color? 1/48, correct. Okay, and if you are working for a manufacturing plant that produces cars, then having such models would allow you to decide what type of production schedule you will have. You know that nobody requires cars with no air conditioner, the chances are 0, then you're not going to produce such a car. Okay, even though you provide the option. Okay, so you can make this more complex. So if you also add another layer for the interior color, then you're going to have more options, and you will have 120 outcomes or 120 types of vehicles. Okay, so again, 3 diagrams allow us to list the outcomes for your experiment. So in such a way, you can list the sample space for your experiment. Now, what type of scenario here we are looking at right now? Is this a discrete or continuous type of experiment? It's discrete, right? Because you can count the number of options. But that's not always the case. Sample spaces with a large or finite number or sample points are best described by a statement or rule of method. Okay, so for example, let's say that the possible outcomes of our experiment are the set of cities in the world with a population of over 1 million. Then you can use such an expression if you don't want to list all the outcomes. So this basically says that the sample space is the set of all x are the outcomes, such that x is the city with a population over 1 million. And I don't know if you have seen that type of notation in one of your previous math courses, but this is a notation that is very common in math when you are trying to state your sets. So again, if you have a very large number of outcomes, you can always try to use this notation to define your set. Okay, so now that we have discussed those concepts, let's discuss this problem. And this is not the lab. Let me give you 5 minutes for you to try to solve this problem, and then we're going to discuss it in class. So try to solve it, and then if you have questions, just raise your hand when I'm start discussing the problem. I updated the list, the sign-up sheet. So if your name is not listed there, let me know. Okay, what will be the sample space for the first, for letter A? Set of integers between 1 and 50 that are divisible by 8. So we know that we're going to have numbers from 1 to 50, but we're going to only list those that are divisible by 8. So we start with 8, 16, 24, 32, 40, and 48. Those are the only numbers from 1 to 50 that are divisible by 8. Okay, so now let's look at your math skills. So you have the sample space is defined by this expression, which is a quadratic function, x squared plus 4x minus 5 equals 0. So basically you need to find out what are the x's that will make that expression equal to 0. And those are your elements of the sample space. Anyone knows which numbers will make that expression equal to 0? Say that again? That's correct. And the way you find that is you need to solve this quadratic equation. Plus 4x minus 5 equals 0. So if you simplify this, this is x plus 5, x minus 1 equals 0. So that will make x equals minus 5, x equals 1. And those are your elements here. Questions? Part C. The set of outcomes when a coin is tossed until a tail or 3 heads appear. So for this one you need to visualize yourself throwing those coins. So you're gonna have only one coin and you're looking at the number of times until a tail or 3 heads appear. So what happened if you throw, the first time you throw the coin is a tail? Then you stop because you already have one tail. So that's one outcome. But something else that can happen is that you have a head and then a tail. You stop. Then you can have head, head, tail. And finally, 3 heads. Those are the only outcomes for that experiment. Okay, so you stop until you find a tail, or you stop until you get 3 heads in a row. Okay, any questions? Part D. The set of continents. So you're basically going to list out the continents in the world. So, excuse me, North America, South America, Europe, Asia, Africa, Australia, and Antarctica. Any questions? And then part E, 1 point for the one. If any of you can tell me what is the answer for part E. Yes, sir. You have the idea, but he uses right concept. So both of you can have a point. So there's no solution because the answer is that there's no overlapping for these set of outcomes. So if you look at the, and please come talk to me at the end of the lecture. So if you look at the expressions, you have 2x minus 4 greater or equal to 0 and x greater than or equal to 2. So if you draw a line and you solve this, this is also you have x less than 1. So this is 0, 1, and 2. So this part right here is basically this area. So you want x to be greater or equal to 2. But you also have x less than 1, which is this area from 1 to the left. So as you can see, there's no intersection for those two expressions, which means that there's no outcome that will satisfy both expressions, which you can represent with the empty set symbol. So this means that set is empty. Any questions? Okay, so this is basically to help you start thinking about how to define a sample space, how to define the outcomes, and so on. So they have more practice here. The next example. Which of the following events are equal? So again, you have to define those sample space for each one of the options. So the first one is already defined. It's 1 and 3. The second one, x is the number on a die. So one of the options for that one is the sample space will go from 1 to 6. What about part C? You got to do the same thing we did for the other problem. So you need to solve this quadratic equation. So this x minus 1, x minus 3 equals 0. So x equals 1 x equals 3. So your sample space is 1 and 3. Part D is the number of heads when 6 coins are tossed. So your sample space will go from 1, 2, 3, 4, 5, 6. Are those the only options? Correct. So you have 0 as well. Okay. So which of the two, which sets are equal? The answer is A equals B. Oh, oops. A equals C. Because this set and this set are equal. Set A and set C are the same. Let's look at the next problem. Can I move to the next problem? Okay. Okay, so this is an engineering firm that is hired to determine if certain waterways in Virginia are safe for fishing. So you're taking samples from 3 rivers. And we need to list the elements of the sample space using the letters F for safe for fish and N for not safe to fish. So using that notation, how many outcomes are we going to have? So 3 rivers, 2 options for each river. Those are 8 outcomes. Because the first river can be safe. So again, F safe and N not safe. So the first river can be safe or not safe, 2 outcomes. Second river can be safe or not safe, 2 outcomes. Third river can be safe or not safe, 2 outcomes. So 2 times 2 times 2, our sample space needs to have 8 outcomes. Okay, so we can list the outcomes using a 3. So for the first river, this is river 1. We have safe and not safe. For the second river, this is river number 2. We have safe and not safe. Same thing here, safe, not safe. And for the third river, same thing. We have safe, not safe, safe, not safe, safe, not safe, safe, not safe. So we have 8 outcomes. So if you list the sample space, then you have S will be equal to 3F, F, F, N, F, N, F, N, F, F, So 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So once you're able to draw your tree, then the only thing that you need to do is to go through each branch and list your outcomes. So 8 outcomes. What is the probability of having all of them safe? Again, 1/8. Okay? So part B, list the elements of the sample space corresponding to the event E that at least 2 of the rivers are safe for fishing. So what do? At least 2 of the rivers are safe. So you're going to have to go through your sample space and find all the outcomes that have at least 2F. So those are the following. S equals F, 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 N, N, F, F, and F, N, F. So what are the chances of having at least 2 rivers that are safe? 0.5. Okay? Because these are all the outcomes that will satisfy that condition. Okay? Part C, define an event that has as its elements the points, all these points. So what will be such an event that have these outcomes? Correct. So if you look, all those events have F on the second outcome. So the event that we're looking at on that sample space is the event of having the second river safe for fishing. Because F is repeated on the second item of the outcome. Any questions? Okay, so now we're going to transition to something.
But
Yes.
last element does not have the second verse.
The last element? You have N, F, N.
No, F. Oh.
This is the answer for part B. Yeah,
We're doing part
you're looking at this.
I thought we're using part B.
No. We're using the set that was provided on part C. Okay? Any other questions? Okay. So what we define here, this is called an event of your sample space. So you're basically listing these outcomes that satisfy a specific condition from your sample space. And that's the concept that we're going to discuss next. It's the concept of event. So suppose that 3 items are selected at random from the manufacturing process again. Each item is inspected as classified defective or not defectives. So we know this problem, we know how to list those outcomes and how to list our sample space. But now, we are interested in the event that the number of defectives is greater than 1. So this will occur if the outcome is an element of subset B, and subset B will come from your original sample space. So we are looking at the number of defectives that is greater than 1. So we're going to list basically all the outcomes that have 2 or more Ds. If we do that, this is our event, or these are the outcomes that satisfy that condition. So we have 3 defectives, 2 defectives, 2 defectives, and 2 defectives. All those outcomes have more than 1 defective. So again, an event is a subset of the sample space, and our event in this case is denoted by set B. Can I move to the next slide? Okay. Now, the complement of an event with respect to the sample space is the subset of all the elements of the sample space that are not listed in your event. So if our event is called A, then we're going to look at all the outcomes that are not listed in A, and we're going to call them the supplement. Okay, so we denote the complement of A using this symbol, A prime. So A will be the event, A prime will be the complement of the event. So if we consider this example, here we have a sample space that have some items listed: book, cell phone, MP3, papers, stationery, and laptop. If we define set A as this, using these four elements, then the complement of that set will be the rest of the elements or the output. So here we don't have cell phone, so cell phone will be part of the complement, and MP3 will also be part of the complement. So if we put together the event and the complement, then we're going to have the sample space. Okay? Any questions? So now we consider certain operations with event that will result in the formulation of new events. Okay, so suppose that A and B are subset of the sample space S of the experimental dosing and data. So we have 6 outcomes that we already know, and we have set A, which is this event, and set B, which is this event. As you can see right now, there's some elements from A that are repeated in B, and there's a purpose for that. And that can also happen. Okay? So note that both A and B will occur on a given code if the outcome in the element of subset is 4 and 6, which is just the intersection of both things. So if we look at the elements that are repeated in both sets, we can call those elements the intersection. And that's another important concept for this topic. Okay, so we can list the intersection of the sets, we can list the elements of the sets, we can list events of the sample space, and so on. Okay, so the intersection is basically the elements that are repeated in both sets. So the intersection of two events, denoted by this symbol, this is another symbol, it's like an inverse U, is the event containing all the elements that are common for A and B. Okay? So another example, we have this set B and another set Z. Then if you look at those two sets, there's no outcomes that are the same. So in such a case, we say that the intersection is empty, is the empty set. Just like we discussed for one of the examples. So no intersection, empty set, that means that there's no intersection between those two sets. That is, B and C have no elements in common and cannot both simultaneously occur. So another definition, two events A and B that are mutually exclusive or disjoint have the intersection equal the empty set. That is, A and B have no elements in common. So mutually exclusive, they cannot happen at the same time. Okay? So such cases, we have the intersection equals the empty set. Okay, so often it's interested of the occurrence of at least one of the two events associated with an experiment. So we talk about the intersection. Now this is a different concept. So let's look at the example. We have A and B, A equals 2, 4, and 6, B equals 4, 5, and 6. We might be interested in either A or B occurring. So it could be one or the other. Both A and B occurring, such an event is called the union of A and B. And will occur if the outcome is an element of the subset. Okay, so in this case, we're going to put together the two sets, the two events, and we're going to create a new set or a new event by combining those two sets. That is called the union of A and B, or the union of the events. So the union of the two events, A and B, is denoted by this symbol. You're going to use U. Is the event containing all the elements that belong to A or B, or both? So we can look at the intersection, which are the elements that are repeated, or we can look at the union, which we put together all the elements. Okay? So in this case, if you combine A and B, this is the union of the sets. So you're going to have 2, 4, 6. 4 and 6 are already here, so you're going to add 5. And this is the union of the sets. Questions? Okay. Let's look at this example. So this table summarizes the visits to an emergency room at 4 hospitals. People may leave without being seen by a physician. That's what we call an LWDS. The remaining people are seen or may not be admitted. So we have this table of information. We have the total. So here's the information for each hospital. So we have 4 hospitals, 1, 2, 3, and 4. And we have the total of patients that went to each hospital. We have the numbers of the patients that leave without seeing a physician, which is here, is this row. The number that were admitted and not admitted. Okay? So the first question is, well, first we need to define A, as I said, be the event of a visit to hospital 1. Then event B is the event that the visit is a leave without being seen. And based on those 2 definitions, I want you to find the intersection of A and B. Okay, so A is the event of a visit to hospital 1. So hospital 1, the number of visits is listed here. This is the information for hospital 1. And B is the event that the visit is a leave without being seen. So the information for that is listed in this row. So what will be the intersection of the patients that went to hospital 1 and leave without being seen? What is the total? 195. Correct. Because that is the point in which both events intersect. Okay? Only 195 patients went to hospital 1 and lived without being seen. Okay, so the first answer is 195. Okay? What is part B? Part B is the complement of event A. So we know that the event A is the event of visit to hospital 1. So the complement of that event will be the patients that visit any other hospital besides hospital 1. Okay? So you have 4 options. You went to the first hospital. That's event A. Now we want to know what is the complement of that event. So we know that A equals 5,292. What will be the complement of A? Say it again. No.
The 22,262 minus the 5,292 is 16,900.
That's correct. So you're going to look at the total. You can do these 2 ways. You can add hospital 2, hospital 3, and hospital 4. or you just look at the total, which is 22,252 minus the number of patients that went to hospital 1. So this is 5,292. This is going to be equal to 16,960. Questions? So again, you need to be sure how those events are defined. So A is the event of visiting hospital 1. The total is right here. So the complement for the total visits will be the summation of the other 3 hospitals, or the difference between the total and those that went to hospital 1. Okay, part C of the union of A and B. Anyone? That, I mean, if you can get that one, I'll give you a point. That's very difficult. You need to show me how to get that number.
Sum of the rows of the BDS added to the hospital visits.
So you're summing this number.
That's
That's correct. Okay, so the important thing here is to make sure that you don't count patients twice. So we are looking at the intersection of 2 events. We know the total that went to hospital 1 is 5,292. And we know the total that went live without being seen. The total will be 953. But if you add those 2 numbers, what that means is that you're double, or you're counting these 195 twice. So you need to subtract that portion. The other way to find the same number is like he explained. So you're going to add 5,292 plus 270 plus 246 plus 242. And that should give you the same number. So you want to count the total of patients that went to hospital 1. And you also want to count the number of patients that live without being seen. But if you add this total plus this total, you will count these patients twice. So you need to avoid that. You will take the total here. These 195 patients are already part of this total. So the only patients that are left to be taken into account are this one, and this one. Okay? So that's why you can do this. Or you can look at the total and subtract that portion. Any questions? I would really advise you to go back and review this problem and come back with questions. It's very important for you to understand this problem. Okay? Okay, so I think I'm going to stop here. We're going to continue next time. Next time we're going to talk about Venn diagrams, which is also a very useful tool to understand the concept that we were explaining today. Okay, so on Wednesday we're going to start from here. Anyone with the sign-in sheet? What is the sign-in sheet? Make sure that you sign.